You ready for this? All right, what we're going to do today is we're going to derive the kinematics equations. All right, now in IB and some other textbooks, they're called the SUVAT equations. I don't really like that name because SUVAT means nothing. But if it helps you remember what it is and what it means and all that kind of stuff, that's fine. So I'm going to go ahead and write that at the top of the board because those are the variables that we're going to use. Now, if you are in, say, AP, you will probably not want to watch this video because it won't be very helpful to you. They use different symbols. The other thing with AP is that AP often includes final and initial positions, which is not included in the SUVAT equations. In the SUVAT equations, we're making a couple of assumptions, and these assumptions are very, very important. Assumption number one is that we are assuming that our starting point at time 0 is our origin. Now, it doesn't technically have to be 0, 0, but it needs to be the origin, the starting point of whatever we're doing. And so it's important to recognize that your initial displacement is 0. And if our initial displacement is 0, then that means that this S right here is your final displacement. Now, if that's our final displacement, final doesn't necessarily have to mean after everything is all said and done. Final displacement could technically be any point during our process, during whatever's happening, whether it be a race or a projectile or whatever else it may be, but it's just the final point that we're looking at right now. Okay? We've got U and V, which are both velocities. U is your initial velocity and V is your final velocity. Again, initial is just when we start whatever our situation is, and you can start in the middle of your situation if you want. Just label that as being the start. And then V is the final velocity, or the velocity at the point in time that we are considering the end. So that S and that V are very highly correlated together, as that those are at the same point in time. Okay? Then we've got A, which of course is acceleration, and T, which is time. Now again, time is going to be the amount of time that is passed between our beginning and our end. So you have to be careful, because if you define the beginning not to be the very beginning of time, or the very beginning of, you know, the ball being launched from the cannon, because you can define your time to start up at the top of your parabola. And if you do that, then you're going to have to change what you're considering time to be. But time goes from the beginning to the end of whatever time period we're looking at. So with that, the first thing we're going to do is we're going to use our definition of acceleration. Okay, now we've defined acceleration as being a change in velocity. So here we go. We're going to go acceleration equals the change in velocity over time. Now this is going to give us an average acceleration. The second thing, first I mentioned that S, we said that the initial displacement is 0 starting at point 0, 0. The second thing that you have to understand is that our assumption is that acceleration is constant. Acceleration is constant, it's not changing. There is acceleration, but it is constant. Okay? If you don't have a constant acceleration, then a lot of these equations are a little bit too simple for using in those situations. This is just a very simple case scenario, and what you'll use most of the time in our IB courses that I'm teaching. So we've got delta V over T. Now, delta V, of course, is just your final minus initial. So we defined that before, V minus U over T. Now, what I'm going to do is I'm just going to rearrange that, and I'm going to solve for V. So I'm going to go ahead and multiply both sides by T. And so I'll have AT equals V minus U. And then I'll add the U to the other side. And generally, you'll see it in the front, but it doesn't matter. So I'm going to have U plus AT equals V. And generally, you'll see V equals U plus AT. I'm just rearranging it, switching the sides, reflective property. And so that is the first of your kinematics equations. The first of the SUVAT equations is that V equals U plus AT. All right, so next. The next one we're going to do is going to deal a little bit with, we're just going to kind of think through it and reason a little bit. We're going to start with the definition of velocity. All right. Now, the definition of velocity, we define velocity, or our average velocity, as being displacement over time. Okay, now that's all fine and good, but how do I actually get an average velocity? Well, if acceleration is constant, then I find an average velocity the same way I find any other average, and I take the two numbers and average them. Okay, so if I take my final velocity, which is v, and my initial velocity, which is u, and I add those together, and then divide by 2, that should give me my average velocity, because the velocity is changing at a constant rate, so the average should be right in the middle of those two. Now, later, when we look at graphs, we'll learn how to use graphs to find slopes and areas and things like that, and we'll be able to show this another way. But for now, we're just using the idea that we understand that an average is half of the sum of the endpoints, and we get the middle number, which is then our average velocity. So our average velocity then is equal to displacement over time. Now, if I multiply both sides by time, I get v plus u over 2 times t, which is s. And that is your second kinematic equation right there. Number 2. Not so bad, right? Okay, so now what we're going to do is we're going to take the two that we have and we're going to combine them. All right? So we're going to combine these two. We found out that s equals v plus u over t, and we know that v is u plus at. So what we're going to do is just take that v equals u plus at, and we're going to substitute that here for v. So what do we end up with? Well, we end up with u plus at, so that's my v, plus u all over 2 times t equals s. Now, this in this format isn't necessarily super helpful, so I'm going to just simplify it a little bit. So I'm going to put the two u's together. So I've got 2u plus at all divided by 2 times t equals s. I'm going to distribute the t to both things on top. I'm also going to distribute the divided by 2. So 2u divided by 2 is just u, times t will be ut. And then here, I'm going to take the at divided by 2, so 1/2 at, and then multiply it by the t, so 1/2 at squared. Okay, now if that was too much at once, then you can work it out on your own. What you could do is you could multiply both sides by 2 to make this a 2s, then distribute the t, and then divide everything by 2. Or you could just divide everything by 2, do that in your first step, and then multiply, distribute the t. Or distribute the t first, doesn't matter. Just go through that process, make sure that you're okay with our third kinematic equation here, which is ut plus 1/2 at squared equals s. All right, one more. All right, we've got 3. We're looking for one more. So this time, what we're going to do, and again, there's no reason why you would ever just do this for the fun of it, but you're just understanding where these things are coming from. So what we're going to do is we're going to go back to our v equals u plus at, and we're going to solve for t. Okay? So we've got v equals u plus at. Let's solve for t, so I'm going to subtract the u, v minus u equals at, divide both sides by a, and I've got v minus u over a equals t. Now, that's not helpful in and of itself because I already basically had that. Okay, so what I'm going to do at this point is I'm now going to substitute that into our the third equation that we found here. We're going to put the t in. All right, so let's see what that looks like. So I put the t in here, so I'm going to have u times t, which is v minus u over a, plus 1/2 times a times v minus u over a squared, which equals s. Now what we're going to do to get that final equation the way that it usually looks, you could actually use this, but why would you want to use that, number 1? And number 2, this is ugly. I just don't even want to have to deal with that. So we're going to do some rearranging so it's a little bit nicer. There's just way too much going on there. Okay, so what we're going to do is just simplify as much as we can, and then we're going to solve for v in the very end. We're going to get v all by itself, and it'll actually end up being a v squared. But let's go ahead and go through that process. So first thing I'm going to do is I'm going to go ahead and square this right here because I don't really want the exponent there. It's kind of annoying. So I'm going to have u times v minus u over a plus 1/2 a. So that'll give me v squared minus 2vu plus u squared all over a squared. Okay, don't believe me, then just go ahead. This is just v minus u squared, which is v minus u times v minus u, which you should be able to do. Use your distribution FOIL, whatever you feel like you got to do, and go ahead and do that. Okay, then from here, we'll go ahead and just work this out. We'll continue going. I notice that the a will cancel out. One of the a's on the bottom. I still got an a down there, but the nice thing is that I almost have a common denominator now. Rather than worry about a common denominator, I'm just going to multiply the whole thing by a. And so I'm going to multiply this side, this whole side, everything by a. And so what that will leave me with is u times v minus u, right? Because your a's are going to cancel out. And then I'll have plus, here the a's are going to cancel out as well. So I'm going to have 1/2 times v squared minus 2vu plus u squared. And then that will be equal to a times s. Don't forget that there's an a there. Okay? And then we can start moving some things together. Honestly, I don't really like the 1/2 either, so I'm going to multiply everything by 2 as well, get rid of the 1/2. And while I'm at it, I'm going to go ahead and distribute this. So I'm going to have uv, which will be a 2uv, because I'm going to multiply everything by u, and then I'll have by 2, and then I'll have u times u. So that'll be minus 2u squared. Again, I'm multiplying everything by 2. Now this one, when I multiply by 2, it'll just get rid of the 1/2. So I'll have plus v squared minus 2vu plus u squared equals 2as. And at this point, I should now just be able to kind of put things together. Again, I said I was going to solve for v, and so I'm going to get the v squared all by itself. You'll notice that I've got a positive 2uv and a negative 2uv or vu, the same thing. So those are going to cancel out. If I get the v squared by itself, it'll just then be v squared equals, I'm going to need to move the u squared over, I'm going to need to move this one over. So that's a negative 2u squared. This is a positive u squared, which leaves me a negative 1 on this side. When I move it to the other side, it will be a positive u squared plus 2as. And so that right there is our fourth kinematic or SUVAT equation. All right, so those are the 4 that you got. What I want you to recognize is, why do we need 4? Why do we have 4? Okay, well, notice that each one of these only has 4 variables. Now that's significant because there are 5 pieces of information here, right? Your displacement, initial velocity, final velocity, acceleration, and time. Each of these equations only has 4 pieces of information, which means if I know nothing about acceleration, then, okay, well, I don't know anything about acceleration here. This one doesn't have acceleration at all, which means if I know nothing about acceleration, I can use this equation right here. If I want acceleration, then I use the one that has acceleration in it. But the neat thing is that really, out of the 5, I'll only need 3 pieces of information, because this equation right here only has 4 variables in it. If I know 3 of those, I can find the 4th one. If I know velocity, initial velocity, and time, I can calculate acceleration. If I know velocity, initial velocity, acceleration, I can calculate time. Note that this one doesn't have acceleration in it, but it does have displacement. So if I know the displacement, if I want displacement, I can use this one, right? So this one has v, u, t, and s. This one right here has u, t, a, and s. And then this one has e, u, a, and s. Okay, each one of these 4 equations uses 4 different variables from up there. So given any 3, I can always find, well, the 4th and the 5th technically. But if I'm only looking for 1 piece of information, then I can get it using one of these. So that's going to be the task over the next day or so, is getting used to, if I have this information, how can I use it with one SUVAT equation in order to find what I'm looking for? And And then how can I use that to get the next piece of information? All right? Just remember, you only need 3 pieces of information. Use the equation that has those 3 variables plus the one that you're looking for. And this will be easy. All right? That's SUVAT equations. Later.